Okay, this video is going to show you how to calculate the center of mass of a non-uniform one-dimensional object like a rod. So this is like a meter stick, except all the different pieces of it have different masses, not the same mass, because it's not a uniform object. It's an object whose density is some function of its length. So first I'm going to draw the object, which is a good place to start. So here's an object. It's in one dimension, x. X equals 0 is at the leftmost end of the rod, which is a good place to always put your origin. Now, if I took a little piece of that rod at the beginning and a little piece of that rod at the end, they'd both have the same mass. So if it were a uniform rod, I'd know the center of mass would be right at the center of the rod, right over there. Okay. However, this is not a uniform rod, so the center of mass is not at the center, and I can't do something that simple. So I need to define a few terms. The first term is linear density. It's going to be very important, and I want to make sure you understand what it is. Regular density, D, let's call it, is equal to mass over volume. And I know you guys remember that back from like 8th grade. So if you know the density of an object, and I have a little piece of volume delta V, I can get the mass of that little piece of a little piece of mass delta M. I can get the mass of it by taking the density and multiplying by the little piece of volume. Density times volume is equal to mass. So there's another quantity very similar to density, which is three-dimensional, called linear density, which is one-dimensional. Now we could call it LD, but that's super confusing because there's a lot of L's and D's when we deal with centers of mass. So instead it goes by the symbol lambda, and lambda is just like regular density except linear. So instead of mass over volume, it's essentially a measure of mass over length. If I had a uniform object, I would just take its mass, divide by its length, and I'd get the linear density. And then, very similar, if I had the linear density and I multiplied by some little piece of the object delta x, I could get the mass of some little piece of the object delta m. Okay, so that's all very good. Now, what's interesting is densities or lambdas don't have to be constants. They can actually be spatial functions. They can vary throughout space. So we're going to define lambda as a function of x, just as the linear density as a function of x. And similarly, lambda as a function of x times a little tiny piece of the object delta x, but I have to make sure it's super tiny, is going to give me the mass of a little piece of the object delta m. The problem is, since lambda is a function of x, if my delta x is too big, my lambda of x is going to exist over too wide a range, and it won't be accurate. So really, I have to make these delta x's and these delta m's as small as possible, super tiny. And if I do that, I turn them into differentials, which are infinitely small little pieces of the object. So instead, I wind up with lambda as a function of x, not times delta x, which is a finite-sized object, but times dx, which is an infinitely small delta x. And that's going to give me a little tiny piece of the mass, and tell me how massive that little piece of the mass is, that little piece of the object is. Okay, so let's draw this out so we can visualize it. Picture dividing my object up into a bunch of little pieces. How many do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 little pieces. Wait, did I count right? 1, 2, 3, 4, 6, 7, 8, 9, 10, 11. Let's make it 12 little pieces. Okay, so I have 12 little pieces of my object, and each one of them, let's say, has a location xi and a little mass delta mi. And it also has a little size delta xi. That's its own width. Well, I could calculate my center of mass right here, right? X center of mass, if this was really my object, could be approximated by I equals 1 to 12, because I have 12 pieces, xi times delta mi. And then I would divide it by I equals 1 to 12 of just the delta mi's. And I would be done. But like I said before, I want those delta m's to be as small as possible, especially if my linear density is varying as a function of x. If m is too big, I'm really only talking about like the average, mass in there. I can't get an accurate value because it's actually even variable within that little piece of the object. So what if instead of 12 pieces, I made it into 100 pieces? I would just have a bigger sum. And now let's imagine I did it into 1,000 pieces and I'd have an even bigger but more accurate sum. Well, so that's the idea of what we want to do here. We want to chop this up into so many pieces that I essentially have my pieces being concentrated at single points, and I have an infinite number of them. And I can't really do an infinite sum because it would take an infinite amount of time to add up an infinite number of numbers. And so that's where the concept of an integral comes in. An integral is what happens when you turn a really big sum into a continuous infinite sum of tiny things. I'll say that again. An integral is what happens when you turn a discrete sum of a fixed number of things into a continuous sum of an infinite number of very, very tiny things. It really is the same thing. It's just represented differently, and there are formulas for calculating them. So if I want to chop this up into an infinite number of pieces, my x center of mass becomes not a discrete sum over 12 things or 100 things or 1,000 things. It becomes an infinite sum over the entire length of the rod, so from 0 to L. And instead of xi delta mi, I come back over to here. I have x, because there is no I, I'm just my location x is where I am, times dm, where dm is a little piece of mass at the location of x. So just to come back to this picture, it's kind of like if this was my dm and it's at a location x, and then I can go along the length of the rod, and at every point x has a dm associated with it. So that's really the same as what's in the numerator over here. These are equivalent. Okay, now I'm going to divide by what's in the denominator, which is the same thing without the x's. So that's going to be the integral from 0 to L of just the mi's, or just the dm's. So I'm going to add up all the little pieces of mass and get the total mass of the object. Okay, well, this seems like something I might be able to do, except I've already run into a problem, which is I'm integrating from 0 to L, which is over position variables, but I'm integrating against a variable that's math. And I don't know how, I know calculus, I don't know how to do that. I can't integrate from 0 to L over an m variable. That doesn't make any sense to me. It's like a nonsensical statement. So I need to be able to represent dm in terms of a position variable that matches my limits of integration, which in this case are 0 to L. Well, I've actually already done that over here. When I said my linear density times a little tiny piece of the thing is going to give me the little tiny mass of that little tiny piece of the thing. So if I represent my dm as lambda of x dx, I get my final equation for the center of mass of an object, which is x, which remember was my position locations, because center of mass is all the masses weighted by position divided by all the masses, times dm, which is lambda of x dx. And now notice I'm integrating, everything's in x and it's from 0 to L, so that makes sense, divided by 0 to L of just dm, so just lambda of x dx. Now I can't perform this integral until someone tells me what function lambda of x is. So let's go on to the next page. Let's practice using this integral in a couple of different little situations. But first I'm going to write it. I'm going to write it in red because it's so important. X center of mass is equal to the integral from 0 to L of x, which is the position, times lambda of x dx, which remember was just your little dm's, your little pieces of mass, so x dm, xi mi, divided by the integral from 0 to L of just the masses, so just lambda of x dx. Let's go on to the next page and look at a couple of situations now. How do I get to the next page? Next page. Here we go. All right, I'm on the next page. Now let's look at some situations. So let's rewrite our equation. XCM is equal to the integral from 0 to L, lambda of x times x dx. I just reversed the order of those because of how I wrote it, but it's the same thing. I'll write it the other way so you don't get confused. X times lambda of x dx divided by the integral from 0 to L of just the dm, so lambda of x dx. Okay, let's look at a couple of different cases. First, let's look at the case of a uniform rod, because we know what the answer to that should be, right? The answer to that should be right in the middle of the rod. So uniform rod means lambda of x is not a function of x. It's just the mass of the rod divided by the length of the rod. Let's plug that in and see what we get. We get XCM equals the integral from 0 to L of x times lambda of x, which is m over L, just a constant, times dx, divided by the integral from 0 to L of lambda of x dx, so m over L dx. And when you have a constant in an integral, this becomes, you can just pull the constant out like you do for a derivative. 0 to L of x dx divided by m over L, integral from 0 to L of just dx. So this cancels. And this becomes x squared over 2. And the integral of dx is just x. X squared over 2 divided by x is just x over 2. And we evaluate that from 0 to L, and we get the known result of L over 2. The center of mass of a uniform rod is right in the middle, L over 2 away from the edge. Okay, let's do one more example now. Let's look at the situation where my lambda is not uniform, it's a function of x now. Let's say lambda as a function of x is equal to something really crazy, like x to the 5th. Oh, it can't be x to the 5th because I need some constant out in front because it needs to have units of kilograms per meter. So let's say it's a, where a is a constant, times x to the 5th. So this is something that really, like, the density picks up pretty rapidly as you move along the rod. So we would expect the center of mass of this object to be way far down the rod because the density is really heavily weighted to larger values of x. X to the 5th is a pretty rapidly increasing function. Let's just use our formulas. So first of all, remember to write the dm equation, right? So dm, we said, was equal to the linear density times dx. That's the most important thing to remember, okay? Just in terms of your own thinking about this. But we can just use our straight equation. XCM is equal to the integral from 0 to L of x times dm, which is lambda of x dx from up here, divided by the integral from 0 to L of just dm, without the x. So let's put it in. That's the integral from 0 to L of x times ax to the 5th dx divided by the integral from 0 to L of ax to the 5th without the extra x dx. And the same thing, I can pull the a's out and cancel them, so I'm just going to cancel them. And I get the integral from 0 to L of x to the 6th dx divided by the integral from 0 to L of x to the 5th dx. When I evaluate that, I get x to the 7th over 7 divided by x to the 6th over 6 using my integral rules. And that's equal to 6x over 7, if I do my algebra, evaluated from 0 to L, my integration limits, which is 6L over 7. And that makes sense. 6/7 L is pretty far down the rod like we suspected. So I hope that was helpful. That's how you calculate the center of mass of a uniform or non-uniform rod. The way you do it is you use this formula. I'm going to write it super big in red, because it is the absolute most important equation for center of mass, which is XCM is equal to the integral from 0 to L of x lambda of x dx, which is just x times the masses added up along the rod, divided by the integral from 0 to L, lambda as a function of x dx. Lambda as a function of x you're given. Remember, we called this dm. This is equal to dm. What's in the basement here is really just the total mass. Once you do the integral, the problem is you don't usually know the total mass, so you have to do the integral to figure it out. And the top was really just the sum of the x dm's added up along the rod. That's it. Keep this as a reference. I know it was a bit of a long video, but I wanted you to have everything to go back to. All right, see you later.